latest research suggests that something dramatic happened in the solar system millions of years ago. An alien star collided with our homeworld and came closer to our central star than the Voyager spacecraft do today. Indeed, the consequences of this stellar visitor may still be felt today. Not only did it drastically alter the orbits of the trans-Neptunian objects, but it also significantly affected the moons of the large gas planets. But how did the stellar passage unfold in detail? Why did it have such a major impact on the structure of the solar system? And what lessons can experts learn from this unique encounter? The two NASA probes, Voyager 1 and Voyager 2, are traveling further and further into space. When it comes to mankind's most remote outposts, there is no getting around the world-famous sister probes, and no wonder. Although the identical spacecraft were only launched in 1977 to gather new information about the outer planets of the solar system, they have now ventured into interstellar space. In figures, this means that Voyager 1 and Voyager 2 have now traveled a staggering 24.6 and 20.6 billion kilometers respectively from the Sun. And while the Voyager spacecraft are giving us unprecedented glimpses of uncharted cosmic worlds, it is worth remembering that the reverse is also true. In fact, a new research study suggests the astonishing conclusion that an alien star once entered the solar system, significantly undercutting the distance that now exists between our host star and the Voyager probes. But what is this all about? And how could this stellar passage help us solve some tantalizing mysteries about our home system? Well, to understand this, we need to venture into the world of the moons of the solar system. And remember that they sometimes exhibit completely contradictory characteristics. On the one hand, there are the satellites, which behave as you would expect. These include the Earth's moon, which orbits our blue home planet prograde, in other words, following the direction of the Earth's rotation. But the bottom line is that this scheme does not apply to all the satellites in the solar system. The outer planetary worlds, such as Jupiter and Saturn, have a strikingly large number of companions that move, to put it simply, in the wrong direction. To use the correct technical term, these moons move retrograde around their planetary fixed points. In other words, retrograde moons orbit against the direction of rotation of their planets, usually on highly inclined elliptical orbits. The contrasting lunar patterns are by no means evenly balanced. Quite the opposite. In the case of Jupiter, experts count 71 retrograde moons, while the mighty gas giant has only 16 prograde moons. In the Saturn system, the difference is even greater. The ratio of retrograde to prograde moons is 100 to 22. Where do the retrograde moons come from? But what is the reason for this unexpected constellation? Well, in a nutshell, experts have long assumed that retrograde moons are, to put it casually, newcomers. Unlike their prograde counterparts, these satellites did not form together with their planet, but in a completely different part of the solar system. Specifically, scientists have located the formation region of these satellites in the distant Kuiper belt, a ring-shaped region beyond Neptune's orbit. This is thought to be the origin of most medium-period comets. The objects that later became retrograde moons must have been ejected from the Kuiper belt in some way and fallen into the gravitational influence of the large gas giants. But what caused it? For a long time, astronomers pointed to the Jovian migration. According to this theory, Jupiter originally formed further out and then gradually migrated inwards. This migration was only reversed by the formation of Saturn, which finally established the king of our solar system in its present orbit. However, the previous passage was not a leisurely stroll, but rather the proverbial bull in a china shop. As Jupiter tore through the early solar system like an oversized wrecking ball, it triggered a mass collision of countless planetesimals, or planet seeds. This effectively wiped out the inner solar system, making way for a second wave of formation of small, gas-poor, rocky planets. Without Jupiter's migration, there may have been no Earth or other terrestrial planets in the solar system. The retrograde moons are also thought to be a relic of this violent excursion. Unfortunately, this hypothesis has a small but crucial catch. It cannot explain all the properties of the moons in question. For this reason, the team led by Suzanne Falsner from Forschungszentrum. Jülich and colleagues from Leiden University in the Netherlands looked for an alternative explanation. They focused on the close flyby of a foreign star, a luminous visit with consequences. As already mentioned, our solar system does not end with Neptune. In fact, researchers now know of several thousand celestial bodies that move through the trans-Neptunian realm. It's even suspected that there are tens of thousands of celestial bodies with a diameter of more than 100 kilometers. But surprisingly, many trans-Neptunian objects move in eccentric orbits that are inclined to the common orbital plane of the planets in the solar system. In order to uncover the reasons for these special orbital characteristics, Falsner, together with her colleagues Matthew Guentz and Simon Porteghis-Zwart from Leiden University, carried out more than 3,000 computer simulations. At the end of the research, published in Nature Astronomy and the Astrophysical Journal Letters, it was concluded that the strange orbits of the trans-Neptunian objects could indeed be due to the influence of a foreign star. The three astrophysicists found that this could even explain the orbits of very distant objects, such as the dwarf planet Sedna, discovered in 2003. Sedna orbits the Sun in a highly elliptical path that takes it as far as 17 astronomical units away from our parent star. If you are a regular viewer, you know that 1 astronomical unit is the average distance between the Sun and the Earth, which is about 150 million kilometers. But if you follow the explanations of Falsner and his colleagues, the aftermath of the close encounter can also decode the characteristics of objects moving on orbits that are almost perpendicular to the planetary orbits. The same applies to 2008 KVI 42 and 2011 KT19, which are moving in the opposite direction to the planets. Specifically, the explanation assumes a star that was slightly lighter than the Sun. More precisely, we're talking about an order of magnitude of about 0.8 solar masses. According to the model, it passed at an angle of about 70 degrees to the planetary plane and came much closer to the Sun than the 2 Voyager spacecraft currently do. While the Voyager spacecraft are now 24.6 and 20.6 billion kilometers away from our parent star, the Sun's stellar visitor could have come as close as 16.5 billion kilometers. This distance of 110 astronomical units is a little less than 4 times the distance between Neptune and the Sun, and has been associated with a series of drastic gravitational turbulences. In the model, the aforementioned turbulence has thrown most of the objects in the outer solar system even further outwards, or out of the solar system altogether, but at the same time, a good percentage of the trans-Neptunian boulders have been catapulted inwards. And while 7% may not sound like much, we're talking about up to 10 million objects 100 kilometers across, or up to 10,000 objects larger than 1,000 kilometers. Some of these, it is thought, were eventually found in the regions around the outer gas giants, Jupiter, Saturn, Uranus, and Neptune, where they were gravitationally captured as moons. The simulation was also able to reproduce the aforementioned ratio of prograde to retrograde moons. In the Jupiter region, the probability that the trans-Neptunian objects would end up in a retrograde orbit was about 30 times higher than for the prograde case. The situation was similar in the Saturn system, and although most of these newcomers were later ejected from their new orbits, enough newcomers remained to form the current group of irregular moons. The irregular moons are characterized not only by their mostly retrograde orbits, but also by the larger inclinations, eccentricities, and distances of their orbits. And if the scientists had their way, the real beauty of their model would be its simplicity. A single cause can answer so many open questions about our home system. What's more, it's even possible that our solar system would never have existed as it does without the close pass of a neighboring star. Another exciting hypothesis is that about 4 billion years ago, a star the size of the Sun passed by the young solar system, tearing up much of the primordial cloud. According to Falsner, the protoplanetary disk was literally mutilated, reducing the mass of the Kuiper Belt region to about 1% of its original mass. What was almost a catastrophe in the distant past is now a plausible approach to explaining the orbits of many trans-Neptunian objects and the sparse population of the Kuiper Belt.